Today I wanted to do a video on does light experience time? And the reason I wanted to do this is I've seen memes on Facebook where people are posting things that light doesn't experience time. And these are a lot of students or other people who don't think too much, who have experienced relativity theory for the first time and are struck by the relativistic effects that they think apply to photons, and they forget all of the electromagnetic theory of the photons, which are electromagnetic waves, and that the electromagnetic theory has to apply as well. So we have two different things. We have, yes, photons have frequencies. Frequencies are cycles per second. So in order to have frequencies, photons have to experience time. And then the relativity part, that any object moving at the speed of light has zero clock rate. The thing is, no object can move at the speed of light. That's impossible. So no object can have zero clock rate. And this is one of the fundamental flaws in the argument, is that people are treating a photon like it's a spherical ball object that's actually traveling at the speed of light, which is an impossibility, so that can't be what a photon is. So this simplified model of a particle traveling the speed of light that people have adopted when they take this idea that photons don't experience time, that it's instantaneous travel from the photon perspective. That's wrong, because you can't have an object traveling at the speed of light. So what we have to do is look at electromagnetic requirements to determine what is really happening. And one of the first things we have to look at with light is polarizable. So it can be linearly polarized in, say, an X or Y plane, or it can be circularly polarized, so it makes a helical course through space. And that requires that the photon be asymmetric. You can't have a spherical ball that's identical in all respects, in all axes, and have it be polarizable. And then in order for it to be polarizable electromagnetically, it has to be an electric charged dipole. Positive charge, negative charge, moving through space, so that they can be polarized linearly or rotating to trace out a helix. So right there we have an idea that photons are not elementary particles, because they're not just a simple ball. They have to have structure, and they have to have charge. Their net charge, of course, is still zero, but they have to have charges. And when you can see this, I'll put up the typical image of an electromagnetic wave propagating through space, where you have an electric wave. An electric wave requires polarization of the medium, which is the quantum field, which is made of particle pair dipoles. So you have to have a rotating dipole in order to make a rotating electric field. And also a rotating dipole produces a magnetic field in its plane of, perpendicular to its plane of rotation. So you get one field going this way and another field going this way. And both the electric and magnetic fields require that you have a rotating dipole in the middle of the photon. And if there weren't a dipole already there, one would be induced, because the quantum field sustains electromagnetic fields even though the quantum fluctuations come and go. So quantum fluctuations are always being replaced by other quantum fluctuations that give the quantum field the correct electric field and magnetic fields so that you get continuity, conservation laws. So the other thing is that you only need a single dipole at one time to get an electric field rotating this way and a magnetic field rotating that way. So by having a perpendicular field, you only need one dipole at a time. Now, the other thing is we have the energy of the photon being E equals hf. The energy is Planck's constant times the frequencies, or h nu if you prefer. So that is the energy of a quantum fluctuation. And that tells us that we have quantum fluctuations in the photon. That's the only way you can get a dipole with that energy. And quantum fluctuations are also massless. And photons are massless. So once again, we have an agreement. And this model was first discovered by Broglie in the 1930s. He realized that if you took a Dirac pair, the electron-positron pair, and put it inside of an electron, or a series of them, then you end up with a model for the electron, or a model for the photon, using electrons and positrons. Now, they were still working on the quantum fluctuation aspects of what is a massless quantum fluctuation. And so his model wasn't developed, and only now does it really fit with what we know about quantum field theory. So what you get is this picture of one quantum fluctuation each half wavelength. In this case, an electron rotating forward while a positron's rotating backwards with respect to the direction of propagation of a photon. And then on the next one, they flip. You have the electron on the bottom and the positron on the top, and they rotate the opposite direction. They have to rotate the opposite direction so that they have net angular momentum. If they had positive angular momentum, you would have something different than a photon. And this would be a photon-like object that also transmitted angular momentum, which may be one form of a neutrino. So we simply have, if we want to actually describe where polarization and electric and magnetic fields come from, we have a model where the photons are made of quantum fluctuations and they're rotating. So we have a simple model where there's a quantum fluctuation each half wavelength. And these quantum fluctuations are in the quantum field rest frame. The center of mass of each pair is not moving. So we have a case where light, the photons, components, don't move. And the same is true with the electric and magnetic fields, which are also polarized quantum field dipoles in the quantum field rest frame. So those quantum fluctuations that make the wave that's part of the photon don't move either. They're at rest with respect to the rest frame. So there really isn't a physical object moving at all. As I said, they're at rest with the rest frame. There's no motion. So there's no relativistic effects on the photon at all. The photon experiences the normal wavelength and frequency in its rest frame. Now, certainly the wave propagates at the speed of light. And because of its properties of the photon wave, it can behave like a particle in a wave. And it meets all the requirements of the photon in the standard model, except that in order for the polarizability to be true and electromagnetic fields to be true, photons can't be an elementary particle. So they're not a ball, a simple object moving at the speed of light. So that interpretation is wrong. So anyway, I hope you enjoyed this video, and I hope you learned something about photons and relativity theory and electromagnetic theory. And if you do, please like it, share it with your physicist friends, subscribe for my next videos, and if you'd like to learn more about quantum field theory, and in particular photon theories, I talk about it in my book, The Zero-Point Universe. And then I talk about things that must be wrong because if quantum field theory is right, in my book, The 100 Greatest Lies in Physics. And if you buy one of my books, that helps me in my retirement, and I hope you learned something. So thanks for watching.